talk about from the exam. Then we will continue today. So the last thing we talked about was really your decomposition. So if A matrix linearly and follows we can write it as A equals QR, where Q is orthogonal, and R is proper. Right? And I kind of blanked when I was talking about it. I said there's lots of useful things about it, but I can't think of any of them off the top of my head. Well, there's similar to the LU decomposition. In that case, the really useful thing about it is if we had, let's say this was a system with a solution, and we had decomposition of A as LU, then we can think of this right here as the vector Y. So we would be solving for the vector Y, and we would get Ly equals B. And because this is lower triangular, we could solve it using forward substitution. So we wouldn't have to do anything like inverting the matrix or doing the full row reduction algorithm. We just go straight to the forward substitution step here. And once we have Y, we can solve Ux equals Y. And in this case, because this is upper triangular, we can use back substitution, and we get a solution that way. So it makes getting a solution easier. In fact, forward and backward substitution is usually something that we can do by hand. It's not difficult. In this case, in the QR decomposition, we have something really similar. If we are able to write A as Q times R, then again, we can say Rx is Y, and we have QY equals B. But now instead of having forward or backward substitution, we have a very easy inverse to compute. Because if this is orthogonal, well, I have to be a little careful. I just said this is orthogonal and not orthonormal. Maybe I should say that it's orthonormal. It's easy to make an orthogonal matrix into an orthonormal matrix. Just divide every column by its norm. So there would be some kind of scaling of the rows. We would be multiplying it by some diagonal matrix or whatever. Anyway, this is easy to compute because the inverse of Q will just be its transpose. If it's an orthogonal matrix and not necessarily an orthonormal matrix, then its transpose, or its inverse may be a transpose times something that rescales the columns. And now we have Rx equals Y, and we can solve this. And now, because this is an upper triangular matrix, we can solve this using back substitution. So again, we have the situation where it's easy to get solutions if they exist. So we'll come back to this near the end of class today using this QR decomposition. But what I want to talk about today, well, I said a couple of times if AX equals B has a solution. So we know that in some situations, we have, well, what are the three situations that we can have? One is under constrained. I think maybe we use another term for this. It's not a full rank matrix or something else. The system is under constrained, which means that a solution exists, but it's not unique. So if we had AX equals B, and B is a solution. I'm thinking about something else along the way. Thinking X equals B is a solution. Then X equals V plus Z, with Z in the null space of A is also a solution. In fact, this gives us our whole solution space. The solution space of any system like this is the null space of the matrix shifted by any solution. So that gives us all the other solutions. They're the one solution that we found shifted by things that are in the null space of A. Okay, then there's, what should I call this? I'll call this, this is the Goldilocks. This is just right. Okay, there's a single unique solution. I think there were technical terms that we used for these, but I'm not going to worry about that. We're just talking about the three situations. And this was AX equals B. A is invertible. It's full rank. Its columns span the vector space in which we're looking for solutions, et cetera, et cetera, et cetera. Okay. And then finally, there's 3, which was over-constrained. In this case, there are no solutions. The word we used for this one was inconsistent. So let's look at an example of an inconsistent system, and then see what we can do with it. There's no solutions. And is there something not quite as good as a solution, but better than nothing? Let's say our matrix is 4, 0, 1 in the first column, 0, 2, 1 in the second column. B is 2, 0, 11. Now, if we wrote an augmented matrix for this, 4, 0, 2, 0, 2, 0, 1, 1, 11. I'm just drawing a dotted line to remind ourselves that it's a augmented matrix. Then when we did the row reduction, what we'd find, we can use this column to clear these two, or this pivot to clear these two. We can use this pivot to clear this one, so we'll have 0 and 0 here. And then something, let's use a star to represent something non-zero. This is the situation that we have with an inconsistent system, right? What's another way of saying this? Another way of saying this is that there's no linear combination of these two. So if we were writing this as AX equals B, it would be something like, try to write quickly. There we go. X1, X2 equals 2, 0, 11. There would be some linear combination of these two columns. That's what we're doing when we're solving this equation. We're finding or system of equations, we're finding a linear combination of this column and this column that gives us this column. It's fairly easy to see that there's no such linear combination. If we were to get this entry out of a linear combination of 4 and 0, then x1 would have to be 1/2, x2 would have to be 0, and then we look at the linear combination for this row right here, we get 1/2 equals 11, which is a contradiction. Not true. I should say it's not true. Okay, so we know this is an inconsistent system, but what can we do instead of trying to find a solution to it? Well, we can look for something in the column space of A that is closest to B. So we can't get an actual solution, we'll get whatever is closest to a solution. And this is called the least squares problem. Why is it called the least squares problem? The reason for this is because what we're looking for is something that minimizes this quantity right here. And of course, when we compute the norm, this quantity, the norm of ax minus b, what we do is we take all of the entries of ax minus b and we square them, and then we add them together and we take the square root. We're looking for the smallest one, so that would be the least one. Now, because we're taking the squares of the entries and adding them together, we're going to end up with a non-negative number. So we can take the square root of it. And if we find something, if we're trying to make the square root as small as possible, then just the sum of the square, we're trying to make the sum of the squares as small as possible too, right? Because they both get small at the same, I don't want to say the same rate, they both get small together, right? So it's good enough just to look at the sum of the squares of the entries in this, and we might say we're trying to minimize this. Minimizing this and minimizing this is absolutely equivalent. So we're looking for the least squares. Okay, so that's where the name comes from, how we do it. I'm going to call the solution that we're trying to find ax hat, or I'm going to call it x hat. And the property that's going to have is that it's going to be less than or equal to ax minus b for any x. So if we picked any x, we would get something that is either the same size or bigger. So our x hat would be a smallest possible solution. Okay, how can we do this? What we will do is we will find b hat, we'll write it like this, b hat in the column space of A, closest to B. And this, in fact, we already know how to do, right? So this b hat is going to be, by the same types of arguments that we used before, this is going to be the orthogonal projection into the column space of A of B. So b hat will be something inside the column space. It will be something that we can solve this equation for. So find b hat in the column space of A closest to B. This is the orthogonal projection of B. And then solve ax hat equals b hat. that's going to be the way we do this. So ax hat minus b will minimize this quantity ax minus b. A second to look at that. Okay, geometrically, what am I talking about? The column space of these two vectors right here is, these vectors lie in R3, they're in three-dimensional space, and there's two of them, so all the linear combinations of them form a plane. So I'm going to draw a classic looking plane. Going through the origin, there's the origin. And maybe this is my vector b. That's the 2, 0, 11. And this is the orthogonal projection into column space. So let's call this, let's just call this column space. Okay. So what do we want to do to solve this? If we remember how the orthogonal projection works, what it gives us is a decomposition of the vector into its orthogonal projection into the space, and then something I'm going to call z sub b. So this is going to be something in the column space of A, and this is something in the column space of A's orthogonal complement. Right? So that's so if this is, this right here, we'll call z sub b. And this is perpendicular to this point, or orthogonal. Whoever that is, could you please mute it?
Yeah.
Okay, thank you. Okay, so what we have is this b hat. We're going to find b hat equals a x hat. So this definitely has a solution because we chose b hat so that it's in the column space of A. So there's definitely a solution for this, at least one, possibly more than one, depending on our matrix A. Okay. So if we look at b minus ax hat, that turns out to be b minus b hat, which is our zb, z sub b. And z sub b is orthogonal to the column space of A, so it's, well, let's write it as orthogonal to the column space of A, but specifically it's orthogonal to the columns of A, right? So if I take the dot product of any column of A and this vector zb, then I will get 0. So what I'll do is I will take the columns of A and I'm going to write this. Write it like this. A1 up to those are the columns of A. And I'll write it like this. It's 0 for this, all the way down to AK transpose B minus A x hat equals 0. Right? So this is a way of saying that all of the dot products are equal to 0. I can condense all of this into a single equation because these are the columns of A, these are the rows of A transpose. And what I get is A transpose B minus A x hat equals 0. So this just encapsulates the fact that the vector that we formed here, this one that's perpendicular to the plane, B minus A x hat, well, it's perpendicular to the columns of A. Did you have a question? Okay. Just adjusting. Okay. So, hoping not to run out of room. So let me do this down here. So I'll expand this equation. I get A transpose B minus A transpose A x hat equals 0. And then I just add it to the over to the other side. And what I get is, so this new matrix A transpose A times x hat equals this new vector A transpose B. And what we've done is we've transformed this into a new matrix vector equation where it's this matrix times this vector equals this vector. And so now we just solve it the way we ordinarily would. But now we're guaranteed to have a solution. And in fact, if we get a solution from this, that will be a solution to the least squares problem. So this is called the normal equation. Or the normal equations, depending on if we think of this as a system of equations or as a single matrix vector equation. Okay, so what does that give us for this one? A transpose A is 401, 021, 401, 021. So what do I get? This is going to be a 2 by 3 matrix, and this is a 3 by 2 matrix, so I should end up at the end with a 2 by 2 matrix. So it'll be 16 plus 1, that's 17. This will be 4 plus 1, that's 5. And then the diagonal, or it's not the diagonal, it's I don't know what you call that. So this is 0 plus 0 plus 1, and 0 plus 0 plus 1. So A transpose A will always be symmetric. And we can check this by looking at what happens if we take this transpose. So you remember, if you take the transpose of a product, it's the product of the transposes, but the multiplication is in the reverse order. So what I get is that this is A transpose times A transpose transpose, which is just A. And so you see that this matrix is equal to its transpose, which means it's symmetric. So A transpose A will always be a symmetric matrix. That's one helpful fact about it. And now A transpose B is equal to 401, 021, 2, 0, 1. 11, 19, and 0 plus 0 plus 11. Did I get that right? 8 plus 11, and 11. Okay. And now we can solve the system of equations by, for example, row reduction, which is something that I very often see when people have a system like this. But of course, if it's a 2 by 2 matrix, it's very easy to get its inverse. So I'll make a little, yeah, sure. And then I will have A transpose A inverse is equal to, I make a little room in front for dividing by the determinant, but what happens? These two swap. And these two get replaced by their negatives. And then we divide by the determinant, which is, just going to double check and make sure I didn't miss this up. Okay, so the determinant is 5 times 17, which is 85, minus 1. So dividing by the determinant gives us 1 over 84. And this is another little hint for doing these computations by hand, which is that whenever you are trying to get an inverse this way, you don't have to include the 1 over 84 in each of these. It's much nicer to look at if you just have integers here and then you have a fraction out in front. It's easier to deal with doing computations as well. Okay, so finally, A transpose A inverse times A transpose B should give us our solution. I didn't write that either. A transpose B. So this is 1 over 84 times 5 minus 1 minus 117 times 19, 11. And just take my word for it. This is equal to 1, 2. So I went through a lot here. Are there any questions? So you can kind of see what I did here. I found that because we were looking for something that minimized the distance between AX and B, then that thing that minimized the distance, something that's in the column space and something that is possibly outside the column space, if we look at the difference between them, the orthogonal projection and the original vector, then the difference is orthogonal to the column space. So this difference right here must be orthogonal to the column space, and so we get this system of equations right here, or this matrix vector equation, which ultimately we rearrange to write as just another matrix vector equation. Okay. Now this system of equations that we end up with at the end, this may not be, we may not end up with an invertible matrix here. So we may end up with something that has something in its null space. And so we may end up with a non-unique solution. However, the b hat that we get, remember that this b hat is unique. And so when we find the solution to this, what we're getting is, well, we're solving, what can I say And this B hat is in fact unique because of the uniqueness of this decomposition that we discussed before. So although this is unique, the solutions that we get may not be unique because this A transpose A may not have linearly independent columns, although it is a square matrix. Okay. So in this situation, there is always at least one solution. So this could be under constraint. So let's kind of bring all of that together in one statement. So we have A n by n matrix, and we have, well, we have B as an n by 1 matrix, or an m by 1 matrix. I'll call it this. Then we have some equivalent statements. So A equation AX equals B has a unique squares solution. So this is equivalent to saying that columns of A linearly independent. Finally, C, the matrix A transpose A invertible. I believe they go through the proof of all of these statements in the exercises, but we'll talk about the more obvious equivalence right now, which is A being equivalent to C.